Section 11.9, we are now taking a look at how to represent functions as power series. So we saw back in section 11.8 that the sum of x to the power of n as n goes from 0 to infinity, if we start to write this out, x to the 0 is 1, then we have plus x to the first, plus x to the second, plus x cubed, and so on, that this would actually end up converging to the sum of 1 over 1 minus x because it's a geometric series, so this would be the sum of the series, for the absolute value of x is less than 1 because r would be our common ratio here, which would be x. Absolute value of x is less than 1. So this is what it would converge to because it's a geometric series. So we could use this now. We can manipulate this to get other series. For example, if we replace x with the opposite of x, we would end up getting 1 over 1 minus the opposite of x, which turns into the sum as n goes from 0 to infinity of the opposite of x to the nth power. And then I could simplify the left side here. This becomes 1 over 1 plus x. And then what I could do is take the negative 1 to the nth power out of this, and it becomes an alternating series times x to the nth power. So this is the series that will represent this expression, which would be the sum of the series. So this is the representation for 1 over 1 plus x. So let's look at our first example, which is another similar expression. So let's write the function f of x, which is equal to 1 over 3 minus x, as a power series about x equals 0. So we will start with 1 over 3 minus x. And I want to get this in the form of like 1 over 1 plus x or 1 over 1 minus x. So because there's a minus here, let's try for that. So I could factor out, because I want this 3 to be a 1, so I'm going to factor out a 1/3. So this will give me 1 over 1 minus, and if I factor out a 3 from an x, that's going to leave me with an x over 3, but I'll keep that in its own little quantity here. So what we're really doing is plugging in the x over 3. So I get 1/3 times the sum as n goes from 0 to infinity. And instead of it just being x to the n, it becomes x over 3 to the nth power. And then this works. So again, this would be a geometric series where r would be x over 3. So the absolute value, I don't know why I wrote r, because I said it. So it'd be the absolute value of x over 3 would have to be less than r, which then tells us if I factored out the 1/3, then took the absolute value of it, I would have 1/3 x, 1/3 times the absolute value of x is less than 1. Therefore, absolute value of x would be less than 3. So we simply just plugged in x over 3 into that formula I gave at the very top, which was the 1 over 1 minus x for absolute value of x is less than 1. So let's look at a theorem now. And this theorem says if a power series, that's what we saw from 11.8, as n goes from 0 to infinity of c sub n times the quantity x minus a to the nth power, has a radius of convergence some value r which is greater than 0, then the function f defined by f of x, which is equal to c sub 0, the c naught here, plus c sub 1 times the quantity x minus a to the first, and so on, is equal to the sum, as n goes from 0 to infinity, of c sub n times x minus a to the n power. It is differentiable. And thus continuous on the interval of convergence, which is a minus r. Remember, it's going to be centered at a, so that would be r units to the left of it, to a plus r. And two facts come from this. The first is we could take the derivative. Since it is differentiable, we would say f prime of x is going to equal the sum as n goes from 1 to infinity. And then we're going to use the chain rule here, because remember, c sub n is a constant. So we drop the first term since it's a constant, which is why I have to say n equals 1. So then this power will come down. So I'll have n times c sub n times the quantity x minus a to the n minus 1. So I'll make a note here. We have to drop the first term, which would be that c sub 0, because it's a constant, so that's why we're starting at 1 right here. Drop the first term since it's a constant. And then 2, we can integrate. We can take the integral of f of x dx. So I'm going to put the constant of integration first in front of it. So there's going to be our c plus. And that would kind of be like that c naught, that very first term that's right here. And then it'll still be the sum as n goes from 0 to infinity. Now again, c sub n is a constant, so I'm going to leave that there. And then we're going to add 1 to the exponent here, so it's going to be to the n plus 1 over n plus 1. And the radii, just to make a little note here, the radii of convergence of the power series in parts 1 and 2 are both r. And we'll see this in our examples. All right, so let's go ahead and find the power series representation for 1 over 1 minus x squared. So we know, because there's a minus here, I'm going to go back to the 1 over 1 minus x. We know that that's equal to the sum as n goes from 0 to infinity of x to the power of n. So our question is, what could we do to try to get this format? Could we take the derivative of this, or should we integrate this? So let's, off to the side, let's start with 1 over 1 minus x, which is equal to the quantity 1 minus x to the negative first. If I were to take the derivative, this would give me negative 1 times the quantity 1 minus x to the negative second times the derivative of the inside, which is negative 1. So then this does become 1 over 1 minus x, that quantity squared. So we want to take the derivative of both sides. So then I'll write it this way. The derivative of 1 over 1 minus x dx is going to be the derivative of this dx. So this becomes 1 over 1 minus x, that quantity squared. This will become the summation, this time as n goes from 1 to infinity, again because that first term drops. And then we'll just use the power rule here. It'll be n times x to the n minus 1. So this converges if the absolute value of x is less than 1. Because we don't have, think of the quantity x minus a. In this case, a would be 0, so it would just be this absolute value of x is less than 1. And if we were to be asked this, the radius of convergence would just be 1. Let's go ahead and just try one more example. Let's find the power series representation or the natural log of 1 minus x. Again, we go back to the fact that 1 over 1 minus x is equal to the sum as n goes from 0 to infinity of x to the nth power. Now we saw what happens when we take the derivative of this. So in this case, this is 1 over something, so the antiderivative of that would give us the natural log. So we're going to integrate. So we'll have the integral of 1 over 1 minus x dx is going to equal the integral of the summation as n goes from 0 to infinity of x to the n. So here we are going to get the natural log. Now because it was already given to us, the natural log of 1 minus x, we're assuming that it's continuous on its domain here, so we don't have to worry about any negatives. So we'll just have the natural log of the quantity 1 minus x. However, because of what's inside here, if we were to take the derivative of this, we would end up getting this times a negative 1, so we need a negative out in front. I'll put my constant of integration first. It's going to become a c. And because I'm going to end up dividing by this negative, I'll call this a c sub 1 for right now. And then this becomes the summation as n goes from 0 to infinity. And I'll use the power rule here, so we'll get x to the n plus 1 over n plus 1. And then I'll divide everything by negative 1. So we get the natural log of 1 minus x is equal to, I'll just call this c now. Then we'll get a minus this summation. And then this would be true for the absolute value of x less than 1. So again, 1 would be our radius of convergence. But I'm going to make a little note here. For c, we're going to note that c is going to equal 0, since when x is equal to 0, we have the natural log right here. That will give us a 1. It's going to equal c minus. So if x is 0, this whole numerator is just 0, so that becomes a 0. So c is equal to 0. Hence, the natural log of the quantity of 1 minus x is equal to the opposite of the summation as n goes from 0 to infinity of x to the n plus 1 over n plus 1. And we were able to write this as a power series.